Welcome. In this video, we're going to discuss how to find the potential function of a given conservative vector field. And here we're given two conservative vector fields. I didn't name them, but let's just name them now. Let's just name them F, big F. And remember, a vector field is conservative if there exists some scalar function, F, such that the gradient of F is equal to the vector field. And remember, when you find the gradient, you take the derivative. So it'd be the derivative with respect to x and the derivative with respect to y in the 2D case. This would be the gradient of f. And in the 3D case, it would be d over dx, comma d over dy, comma d over dz. Oops. There we are. So if we want to find the potential function, we have to undo what we've just done. And what we've just done is derivatives. To undo the derivative, you do the opposite, which is integration. So let's go ahead and integrate. So I'm going to take just my x component. So in essence, this is like having g of some function g, gi plus hj equals f. So I need to integrate each of these functions. I'm going to go ahead and integrate the function g with respect to x. So that's the integral of 2y dx. This is 2xy plus a constant. Now let's do the same for h. So the integral of h dy is equal to the integral of 2x dy. So that's 2xy plus some constant. And this is some constant function. So now to finish off, I need to make a little space, so bear with me. Now that I've gone ahead and made a little space, I know that my potential function f of xy is equal to, well, what do these have in common? This 2xy plus some constant function. And by the way, these could be different constants. This could be C1, C2, but I'm going to combine them together to just make C. All right, let's do the same thing for part B. Now for part B, we have three functions. So I have f is equal to a, comma, b, comma, c. So I'm going to first integrate a with respect to x. So a in this case is 2xz. And if it helps, I'll do this, I'll color code this. So this is dx. And this becomes x squared z plus a constant. Let's go ahead and do this for b. So for b, I'll do this one in green. I have the integral of b dy, well, that's equal to the integral of 2yz dy. So this is just y squared z plus a constant. And as usual, I'm going to scooch things around. I always underestimate the amount of space I need. So let's look at this third one now. This one will be in orange, c. So I have the integral of c dz. That's equal to the integral of x squared plus y squared dz. That's x squared z plus y squared z plus some constant. So let's look very carefully at what these all have in common. And right away I see x squared z. I also see y squared z. So that tells me that my potential function in this case, f of x comma y comma z, is equal to x squared z plus y squared z plus some constant. So this is a good time to emphasize that these potential functions vary only by some additive constant. That's it. All right, please keep calm and math on.